this picks it up. Should be on. All right, now we're good? I can hear myself, cool. All right, thanks for letting me know. That's what you guys should be doing. I saw something, we're gonna go off the script. It was like a 2-hour video of a guy lecturing. I think it was somewhere over in Asia, and no one told him he was muted for the entire 2-hour lecture. So don't do that to me, please. All right, so let's jump into where we left off. We were kind of talking about this multiplication rule, where we were calculating these conditional probabilities, right? So this is the idea that we're given that this event A has occurred. Now what's the probability of B? Right? And we talked about some examples, kind of how this works, and why that conditional probability can be rewritten as the intersection of those two events divided by the probability of what we're conditioning on, okay? We saw kind of examples with the contingency table, and I want to try to kind of look at this a slightly different way than last class. So we'll pick up, I believe we left off with this example where we said, look, if I want a conditional probability, I can't directly get that from the table, but I can rewrite it as the intersection of two events divided by what I'm conditioning on. So we grab that intersection of those two events, which is 0.2, the probability of the event we conditioned on, what's on the right-hand side there, so that was 0.5, and we get this conditional probability of 0.4. So notice, if I just wanted the probability of R1 here, the entire experimental outcome space is 1. So it's almost like if I drew this, I'd have this huge entire experimental outcome space of 1, and the circle that represents R1 would be 60% of that space, right? Or a probability of 0.6 out of that 1. Okay? Once I condition on C2, I'm now thinking about my entire experimental outcome space. Well, I'm telling you, I know C2 has occurred. I don't know where in C2, which outcome, but we're in C2 somewhere. So my entire experimental outcome space essentially went from 1 to 0.5. Right? And of that remaining 0.5 space, only 0.2 of it would be outcomes that are in R1. So essentially from like where we're starting out without any information, and R1 made up like 0.6 of the one space, or 60% of the space. Now it's only making up 0.2 out of 0.5, or kind of 40%, a probability of 0.4 of that space. Okay? And if we condition on different things, let's say instead, oops, before we get to independence, let's say I take this exact same thing, paste it here. Let's make it a little bit bigger so we can read it. Okay, move this thing out of the way. So now we're thinking about, let's say instead of conditioning on C2, I'm now looking for still the conditional probability of R1, but I'm conditioning on now C1. So all these would change to C1. Right. Now what I'm thinking about is I'm telling you now that C1 has occurred. So we have still limited our space from 1 down to now just this remaining space of 0.5. Of that remaining space, how much of it is also in R1? 0.4. So a much larger proportion of the remaining space is now also in R1 as opposed to before when we conditioned on C2. Right? So it's almost like we're kind of looking at a smaller space of these experimental outcomes, and potentially of that remaining space, a higher or lower percent or proportion of it is now in that event R1 that we were concerned with. And here the numbers would change, right? So now R1 and C1, that was going to be 0.4 out of whatever the probability of C1 was 0.5. Oops. Right. So of that remaining space, about 80% of it was in R1. So notice when we condition on different things here, those conditional probabilities of the same event, right? We're still looking at R1, but we've conditioned on different things. Those probabilities can be very different. And I think I talked through some examples, kind of imagine R1. I think the example I gave last class was that someone wants to support the legalization of marijuana, and C2 here maybe is that they're registered Republican, C1 would be a registered Democrat, right? And we would expect those probabilities to be very different, okay? So kind of a little bit of review and just thinking about this in a slightly different way. But using this idea of conditional probabilities, we're going to talk about a definition, which is independence, okay? So we say that two events are independent if the unconditional probability of an event, so the unconditional, we're not conditioning anything, it's just the probability of A, if that's equal to the conditional probability of A, right? So once we condition on B, if the probability of A is the same as when we conditioned on nothing, we'd say these are independent events. So this is the idea that if you give me this additional information, it doesn't change the probability that A occurs. Okay? So I'll give an example, at least that makes sense to me. So we'll kind of stay with a political example because I think it makes it a little easier. So let's say the probability of A, maybe we're just interested in what's the probability that somebody has, I don't know, blue eyes. Okay? I then say, okay, what's the probability they have blue eyes conditioned or given that event B has occurred? And event B is that they are, I don't know, a registered Democrat. Right? Well, knowing that someone has blue eyes doesn't tell me anything about their political leanings. And so why would that change the probability that they have blue eyes if I have this additional information that's completely unrelated to whether or not they have blue eyes, right? So this is the idea of independence. You gave me some additional information that this other event had occurred, but these two events aren't related at all. So it doesn't change the probability of what I'm looking at, okay? All the examples I kind of gave you last class were things that were dependent, right? Once you knew that event B had occurred, the probability of A would change a little bit because they depended on each other. Right? Independence is if they don't depend on each other at all. So if we go back to our multiplication rule, when we had it kind of rewritten a little bit so that we were solving for the intersection, here we can now say that, all right, if we can write the intersection of two events as the conditional probability times what we're conditioning on, well, if two events are independent, I could actually plug in for this conditional probability, right? If they're independent, I know the conditional and unconditional probabilities are the same. I could just plug in the probability of B here, right? The unconditional probability. Okay. And I'll kind of relate this to something I'll talk about here in just a second. But this simplifies our equation to when we want to find the intersection. If they are independent events, right, I can just multiply the probability of seeing each one by each other. Okay? Now, mutually exclusive isn't the same as independent, right? Mutually exclusive was that they couldn't happen at the same time, which made our intersection 0, right? There was no overlap. Independence doesn't mean that you can't see these things happen at the same time. They can be non-mutually exclusive. You can see both of them happening. It's just that they don't depend on each other, right? So, I'm thinking about my eye color example. If I just look at the general population, let's say the probability that someone has blue eyes is about 0.1. Okay, so out of every single person in the U.S., I have everybody in front of me. I don't know where we're going to do this at, but everyone's in the same place. You count up everybody. The probability that someone has blue eyes is 0.1. Right? So maybe make it easier. Maybe think about we only have 100 people, right? And 10 of them would have blue eyes. I then say, okay, now I'm going to condition on whether or not the person is a registered Democrat, right? So maybe that's only 50 of my remaining people, okay? However, of those remaining 50, that proportion of blue eyes looks the same as the entire group, right? Because those two things aren't related. So I'm just looking at a smaller space, but the proportion of people that have blue eyes within registered Democrats, registered Republicans, is still going to be right around that 0.1, right? The same as if I looked at the entire population. And that's the idea of independence. So I can still see someone be a registered Democrat and have blue eyes, right? They're not mutually exclusive. Right? So our equation will kind of simplify to this, which using a contingency table with this in mind and kind of the definition of independence, let's see how we would check to see if two things are independent. So I've got this contingency table here. We know that this is the definition of independence, that the unconditional probability is equal to the conditional probability. Well, here, what's the probability of A? Probability of A is 0.6. Right? How can I find this conditional probability? Well, we said last class and kind of starting out today, it's the intersection of these two events divided by what I'm conditioning on. So what's the intersection of A and B? 0.15. What's the probability of B? 0.25. So 0.15 of the remaining 0.25 space is in A. So I calculate that, ends up being 0.6, which is exactly what the probability of A was, or the unconditional probability of A. So that's one way we could check. Those two are the same, so we would say they're independent, right? This is the definition definition of independence, and it held. Okay. We could have checked it this way as well. What's the probability of B? 0.25. What's the conditional probability of B? Well, we could rewrite that as the intersection divided by what I conditioned on. The intersection is 0.15. The probability of A is 0.16. 0.15 over, sorry, I think I said 0.16 is 0.6. So 0.15 over 0.6 is 0.25, which was the exact same as the probability of B. Right? So I can check it either way, and both would have led me to figuring out that these two events are independent, right? If A is independent from B, B is independent from A here. Okay? Any questions on anything up to this point? Just make sure that these are all just about me being muted. Yep. We also said that if they're independent, that this should be true. The intersection should just be the probability of each event multiplied by each other. So let's see if that holds here. We can check that. Right. What's the intersection of A and B? 0.15. Is that equal to the probability of A, 0.6, times the probability of B, 0.25? We plug that into our calculator. Sure enough, we see that it is, right? If I just take probability of A times the probability of B, I get 0.15, which was the same as the probability of the intersection. So any of those three ways you can use to check for independence. Right? The first one was just kind of more of the actual definition. This one is going to be a byproduct, right, of two events being independent. And you could check it this way. I won't ever I'm not going to quiz you or throw a question like this in the exam. But one thing I wanted to mention is what ends up being true is that if two events are independent, like A and B are independent here, the complements actually end up being independent as well. So if I check to make sure that the complements are independent using this method, probability of A complement 0.5, probability of B complement 0.75. If I multiply those two by each other, I get 0.3, which is the same as the intersection of the complements. So if two events are independent, their complements end up being independent as well, right? Any questions on this? Okay with this? All right. So those are different ways we can check for independence. Now, if two events are independent, it makes some things kind of easier to calculate. So think about if we have independent events, think about flipping a coin, okay? So we know if I flip a coin, the probability that it comes up heads is going to be 0.5, right? Probability it comes up heads is 0.5, probability it comes up tails is 0.5. It's a fair coin. Over the long run, if I keep flipping this coin enough, right, maybe I flipped it 5 times, I could end up seeing 5 out of 5 heads, right? But if I flip this 100,000 times, I'm going to end up with a proportion of heads that's right around 50%, okay? So what we say is every single time I flip this coin, right, each coin flip is independent from the previous one. Right? So if we have independent events, then the unconditional probability should be the same as the conditional. So we'll kind of use this to think about gambling a little bit here in some situations this will apply. So let's say I get a really long run of tails. I flip this coin and I see it comes up heads 9 times in a row. What's the probability on that 10th coin flip it comes up heads? Still 0.5, right? If they're independent events, what's occurred before doesn't affect the current coin flip. So this would be the idea that we're really thinking about conditioned on seeing the event that I got 9 heads prior. What's the probability I see heads in the 10th? Well, if they're independent, that's just the same as the probability I see heads, the unconditional probability, right? So, you know, I at one point did some work in Excel where I used some stuff to simulate kind of coin flips. And then I looked at the conditional probability. So every time I saw only 1 tails, right, in a row, what's the probability on the next coin flip I saw heads? Pretty much 0.5. If I saw 2 tails in a row prior, what's the probability I now see a heads? Still about 0.5. 3 in a row, what's the probability? 0.5. 4 in a row, 0.5. And right, it's really close. It's not exactly 0.5 because I didn't flip this an infinite number of times, right? I stopped at 10,000. Okay? But you kind of get the idea. It doesn't matter how many previous successes we saw, the probability of heads is always 0.5. Okay? So there's this old example. There's this casino, where is it, in France or Monte Carlo? It's in France, right? Shows how much I know about world geography. And you know, there's a green space, but think about it as when you spin this roulette table, it's essentially 50% chance that this little ball lands on a black square and a 50% chance it lands on a red square. I don't know how familiar any of you are with this particular casino game, but the general idea is there's a 50% chance when this wheel is spun that you see red, 50% chance you see black. Okay? Each spin is independent from the previous. Okay? So every single time, the probability that you see it come up red should be 50%. Okay? So black came up 26 times in a row, right? Then this one situation. Very unlikely. We'll actually think about how unlikely it was in a second. And what ended up happening was people started betting on red because they fell victim to this gambler's fallacy. They said, well, look, after the 10th time that they spun this wheel and it came up black, in their minds, it should be 50%. So the 11th, it has to be red, right? It has to even out. But each single spin, just like coin flip, was independent from each other. So the probability every single time, half the money should be on black and half the money should be on red. But people started betting on red because it said, well, black's come up 10 times in a row, it has to come up red on the 11th. Well, it's been black 11 times in a row, it has to come up red on the 12th. And kind of continued this betting habit, and black kept hitting till 26 times in a row, right? So, you know, I mean, the casino made tons of money off this because people kind of fell victim to this incorrect gambling habit, or gambling fallacy, we call it gambler's fallacy. You know, and so the casino likes this because if people don't understand the idea of independence, you can make really bad decisions, right? We see this in a lot of gambling habits. If we look at the data, people fall victim to this all the time, right? So let's think about it. Black came up 26 times in a row. We'll go to Excel here, but I'm going to just use it as a blank sheet here because it's easier to do. So we think about the probability that it comes up red was 0.5, right? So what's the probability it comes up red, or sorry, black was, it came up black. So the probability it comes up black is 0.5. What's the probability it comes up black on 2 consecutive spins? Well, if they're independent, my events are essentially what's the probability I see black on the first spin and I see black on the second. If they're independent, I should just be able to calculate that by multiplying the probability of A times the probability of B, or the probability to get black on the first spin times the probability to get black on the second spin. So there we would just be thinking about the probability it comes up on 2 consecutive would be 0.5 times 0.5. What about 3 in a row? 0.5 times 0.5 times 0.5, right? What about 26 times in a row? Essentially, 0.5 to that 26th power, right? So how unlikely was it that we saw black hit 26 times in a row on this roulette wheel? Well, it would be 0.5 times 0.5, 26 times, or 0.5 to the 26th power. So move this decimal point 8 places to the left, so 0.000001, right? As incredibly low chances. But you can do things like this. You can figure out the probability that something happened this many times in a row if they're independent events, right? And it's simply, if you're multiplying that same probability by each other, it's just the original probability to whatever power you're interested in. Right here, 26 times in a row, so to the 26th power, okay? Any questions on that? Shouldn't be too bad. All right, so we've worked through a lot of stuff with these contingency tables and different probabilities. I think I have a kind of reminder of the rules here right after this Excel example. But we're going to look at Excel and we're going to actually say, well, I'm going to build my own contingency table. So usually, like I've been showing you these really easy kind of event A and B contingency tables, right? But where do those numbers actually come from? Well, a lot of times we'll have those contingency tables, but they're going to be built from some underlying or original data. So I have this data set. Let's see, it's like all these different industries, right, in different years. And I'm looking at them and thinking about, okay, what was the union membership in those industries in that year? What is the union members' weekly earnings? What are non-union weekly earnings? And here I just created a variable which was, okay, what's the difference between union and non-union earnings? So all I did here was take union minus non-union earnings. Right? We think about with union power, hopefully these workers are usually able to bargain for larger salaries or higher wages, right? In fact, if we look at that difference variable, there's a couple that are negative, but for the most part, everything's positive, right? The unions in most of these industries are actually earning more than their non-union counterparts, okay? So if I think about maybe in different industries, there's a higher percent of union members. Let's think about if I'm trying to hire a worker and 100% of the workers in that industry are in the union, well, I have to pay union wages, right? But if it's only like 10%, well, I'm not going to hire a union member because they're going to cost me more, right? They're able to bargain for higher wages, so I'm just going to hire a non-union member for a lower wage, right? So we might think about the percent of these industries that are union workers might influence what that wage differential is. If we're all union members, we can have a lot of power to bargain our wages up with these companies, okay? So we have these two variables. Now, you don't always have to do this, but just to get an idea, let's look at some averages. So the mean union membership, we'll go over here, equals average. Here's my membership. Control Shift down arrow or Command Shift down arrow on a Mac, hit enter. All right. I'm going to do this for union earnings. Oh, which one was that? I think it was E. And then we're going to do non-union earnings, which is right here. And this is just to get an idea about what the data we're looking at. And then the average difference we'll find right here. Okay? So on average, across all these industries in these different years, about on average, an industry has 10% union members, right? And that varies from union to union, but the average is 10. Right? The difference in union non-union earnings, the average difference is about $118. Okay, so union members earn on average about $118 more. And I believe these are weekly earnings. Okay, I'm going to get rid of this and put it up here. So I'm going to create some cutoff values here, and I don't want to use different ones, so I'll try to remember. So let's say I use the cutoff of 10, and so thinking of 10 and 100. I'm just going to put those values there for right now, and I'll kind of explain a little bit more about why and how we'll use them. So if I look here, I've set up this contingency table, and I've thought about two events. One event is the union membership above 10% in that industry? Or kind of the complement of that would be, is it below 10%? So I've essentially set up my events B and B complement. My event A, I said, is the difference in union, non-union earnings $100 or more? That's my event A, or A complement, is it less than $100? Okay? So I've set this up just like those contingency tables we had. It's just I've actually given names to what A complement, B, and B complement are. And I use these cutoffs, right? What you should be using here really just depends on what the problem is. I try to choose something around the average, so I can think about this as like industries with above average union membership, industries with below average union membership. But I just want to choose not the actual average, I just want to choose a number close to that, okay? Just to kind of make this a little bit easier to think about. So if I want to build this contingency table, what I'm thinking about is, okay, how many industries have 10% or more union membership and $100 or more differential in union, non-union wages? So I'll count the number of industries where that is true, that both of those things are true, right? A and B are true there. Once I have that frequency to turn it into a probability, well, it's just like what we were doing essentially when we looked at frequencies and changed them to relative frequencies. All we did there was divide by the total number of observations. So those relative frequencies were really representing proportions or probabilities that we were creating based off of the data we had. So the first thing we'll do is we'll count the number of industries where both of these things are true. So we'll use something we've used already, which is that count ifs. Because essentially we want to count the number of observations where the first thing is union membership above 10%. So we'll have to select that variable. So we go over here. Our union membership variable is right here, right in column C. So I'll select that entire column, Control Shift, hit the down arrow. You got to scroll back up here, which is kind of a pain. But now that reference is there to use that whole column of data. I'll then put a comma. The next thing I need to tell it is take that variable and only count the observation if, right, union membership is greater than, right? So we'll put that in quotation marks. Put an and sign, greater than 10%, right? And then have that cutoff of 10% up here in this cell, okay? Now, that was the first thing we wanted to check to see, to count if it was true. But we wanted to count them if they had above 10% union membership and the wage differential between union and non-union members was $100 or more. So the second thing we want to do is go look at this difference variable and say, we only want to count it if that difference in earnings is greater than 100. Actually, I said 100 or more, so I actually want greater than or equal to 100. So you could select this again, but on a laptop especially, and especially if I didn't have my mouse with me, it's kind of a pain to scroll back up. Well, notice if I know the column this is in, the data is going to go from 2 to 736 as well. So I'm just going to type it in, H2 through H736. Right? You could have selected it, with your mouse or using the control shift, but this is for me a little bit easier, so I don't have to keep scrolling up and down. So here was the first thing I wanted to check using this variable. Now I want to use this other variable and only count it if it's greater than or equal to, right? Use the and sign. And my cutoff for the income difference was this $100 that I had up here. Okay? Close my parenthesis, and this should count the number of industries that have $100 or more difference in union, non-union member earnings and have union membership that's above 10%. Okay? So this is why I said, when we first used the count ifs formula on building the histograms, it was weird because we were selecting the same variable here. Well, we can use that count ifs when we want to check to see if two different variables meet different criteria as well. Okay? So if I hit enter here, 220 of those industries that I have in my data set meet that criteria, right? Have 10% or higher union membership or $100 or more. And actually, I think I forgot my equality here, right? Because it's 10% or higher, so greater than or equal to. Now, I'll show you kind of a shortcut to filling out the rest of this table. So I could type this in, again, down here using the count ifs. Now I want to check, is it greater than or equal to 10%? And is the other variable less than 100? Well, instead of typing everything in, I'm always going to want to use the same range of data. So I'm going to freeze that. So once again, F4 or FNF4, if you're on a Mac, Command T, puts those dollar signs there. We'll do the same thing to the other variable. But also notice, my cutoff value should never change here either. So I'm actually just going to freeze these as well. Okay. Now when I copy this over, it should give me the exact same value, right? Because nothing should change here, right? Now, another thing you could have done, instead of, let me see, let me get all the dollar signs off. Let's see if it'll do this. It's probably going to yell at me. Yeah, it just doesn't like that. All right, so let's say I had it entered in without dollar signs, right? And let's say I want to copy that to the other cells. If I highlight this and then Control C, or if you just copy it, hit enter to get out of the cell. Now if I go over here and I click on that cell and I hit paste, if I use that copy paste, right, it doesn't actually update my cell references. So I can do it either way. I can use that copy paste, or I could freeze everything and just drag it over and copy it that way. Okay. So I'm just going to drag this over to copy it. Also, I changed the size of my mouse, so hopefully this is a little bit easier to see me moving. So I've got the same value, but that's because I haven't changed that criteria. Because in here, what I actually want is union membership, I want to make sure we can see this, below 10%, and is that difference in earnings $100 or more. So now instead of being greater than or equal to 10%, I actually only want to count it if it's less than. Right? Now I still want to check to see if that variable of difference in earnings is greater than or equal to 100. Right? So should be okay. Now I'll hit enter. Okay, so I'll go down here. Here I want to see, is union membership greater than or equal to that 10%? So that's good. But now I want to check to see if that difference in earnings variable is less than 100. So not greater than or equal to 100 now, but less than 100. So once I copy this over, I'm basically just going through and making sure those equality or those kind of inequality signs are matching up with the row and column heading. Okay? The last one I have, I want to make sure that it's less than $100 and less than 10%. So I'll change both of these to a less than sign. Okay? Any questions on that process? So I've got my frequencies now, right? So now how can I get the totals? Well, how did we say we do it when we had probabilities? How could I have reproduced the total column? I said you could add down the columns or across the rows, right? Think about it this way. If I want the number of industries, this total represents the number of industries with $100 or more wage differential. Right? So if I count the number of industries that have $100 or more wage differential with 10% or higher union membership, and the number of industries with $100 or more wage differential that have below 10%, well, that covers everything. I've now counted every single industry that just has $100 or more wage differential, right? They'd have to meet one of these criteria. Their union membership would either have to be 10% or higher, or it would have to be below 10%. Right? So we said we could add across the rows, so I can use that sum function just to add these values up. I can then copy that down. It'll add these two up for me. And I also said to reproduce the totals down here, you can add across the rows and down the columns. Right? So I'm just adding these two values up. Right? With that sum function, go over here. Now if I think about what should I be able to reproduce here, well, if I count all the, well, I'll do it this way. If I count the industries that have 10% or higher union membership, and I add to that the number of industries I have in my data set that have below 10%, that's going to count every single industry that I have in this data set. So if I add these up, these totals up here, I should end up with my total number of observations. Okay? So I hit enter. 735. How could I check that? What was a function that we used just to count the number of observations? Equals count. Yeah, same. I kind of was trying to allude to it there. We just use that count function. I go over here. I can use either variable. Control Shift, Command Shift on the Mac down arrow. Hit enter. It tells me the number of observations. My total here matches it. That's good. That means I didn't make a mistake. If I had, let's say I forgot the equality in this very first one, notice I would have been missing a couple observations. And if I use this as a check, it lets me know, okay, I made a mistake somewhere. And if I'm only a couple observations off, it probably means I made an error with the equality signs. So let's put those back in, and you know, that was the error. Okay. Any questions on any of that right there? Okay with that? All right, let me make sure there's nothing in the chat. Okay. So, all right, this is great. What the hell are we doing? We're trying to get probabilities, and I've got all these numbers over 100, right? Well, I said if I know the number of industries that meet this criteria, to turn that into a probability, it's just 221 out of the total number of industries, out of 735. So what I'm going to do to create my contingency table is I first built this frequency table, and then I'll just take every frequency and I'll divide it by the total number of observations. Now, when I copy this over, I want K9 to become L9, but I always want that total number of observations to stay the same. So I'm going to throw some dollar signs there and freeze it. So that will always kind of keep dividing everything by the total number of observations. So I'll copy this over. I'll copy this down. And now I've got my probabilities. That easy. Right? Once I get my frequencies, turning them into probabilities should be a pretty easy step. Now notice, hopefully when we get down here, I'm taking the total number of observations divided by the total. I should get 1 here, right? That's what I should always have. Right? So if I don't have 1 here, I made a mistake. Right? Excuse me. Any questions on that? Like I said, that shouldn't be too bad. Okay. Well, now, this gives us some probabilities to start playing around with. And just for the sake of the way these look, nope, wrong way. I'm just going to put them to 2 decimals just so it doesn't look too crazy. But the nice thing is, even though it looks like 2 decimals, it's still stored out to whatever the decimal level is. So let's say I just want the probability that an industry has 10% or higher union membership. So I would go equals, where would that be? The probability they have 10% or above union membership. So if I want the probability that's 10% or higher, what should that be? Yeah, I just remember, we go down to the total. The total columns represent the probability of whatever their column or row heading is. So the probability that someone has 10% or higher union membership in their industry, we just go down to that total, right? I could just click on that cell, hit enter. Right? Now, what if I wanted the probability of being 10% or higher and having a wage differential that's $100 or more? Okay. So what cell would that be in? Well, it's a little tricky because 10% or above, but that or is kind of within our event. So I want having 10% or higher and a wage differential of $100 or more. So wage differential of $100 or more and 10% or higher, right? My top 4 left cells, those are what represent the intersection. This and this. Okay. Or maybe I should say this and that, I don't know. So we can use this contingency table just like we were doing before. So let's think about some conditional probabilities. Given that I'm looking at an industry that has 10% or higher union membership, what's the probability that I see them have a $100 or more wage differential? Well, if we want a conditional probability, we said it's the intersection of these 2 events. So there, $100 or more and 10% or higher. And then we divide that by what we condition on. So what we're conditioning on is that there's a 10% or higher union membership. So the probability of that we have down here. Right? It's kind of using these two probabilities we found earlier. Hit enter, and I get, okay, if I know that an industry has higher than 10% union membership, the probability that their union members make $100 or more than their non-union members is about 76% chance, right? Or a probability of 0.76. However, what if I say, okay, now I'm conditioning on or telling you the industry has low union membership, below 10%. Well, it's still going to be, right, it's a conditional probability. It's going to be the intersection of those 2, so $100 or more and below 10%. And I'll divide by what I'm conditioning on, which is the probability that it's below 10%. So now if I tell you that the industry has low union membership, the probability that there's $100 or more wage differential between the union and non-union members, it's fallen to only about 40%. And this is the idea that's kind of telling us that, yeah, these are, looks like these 2 things might be related because the conditional probabilities change quite a bit when I'm conditioning on these different events, right? If I know that there's more union members in an industry, they're going to have a little bit more market power. They're going to be able to have a higher likelihood of bargaining for this large wage differential. If I'm in an industry with low union membership, they don't have as much power, the probability they can bargain up to this $100 or more wage differential, not near as likely, right? What, 35% lower, actually. Okay. And, we could do things like check for independence here using our different methods. So, for example, let's say, it should be that the intersection is the same as the probability of the events multiplied by each other. So if I take 0.55 times that 0.39, the probability of $100 more wage differential times the probability of 10% or higher union membership, that should be equal to the intersection of those 2 events if they're independent, right? So I look there, well, that's not 0.3, so I will kind of think about these are not independent events, right? Because the product of the 2 events, probability of A times probability of B, is not the same as the intersection of those 2. Okay. Are these events mutually exclusive? Should be able to tell me from that contingency table. Is having 10% or higher union membership and $100 more wage differential, are those mutually exclusive events? If they were mutually exclusive, what value should I see here for their intersection? 0. So are they mutually exclusive? No, because this is not 0, right? More often than not, they're not going to be. Like, mutually exclusive is somewhat rare, right? And we're looking at things. So that's kind of how we would build our own contingency table. You might be asked in the next Excel assignment, kind of after this week. I might post an Excel assignment where you have to kind of build your own, and then you're kind of asked to do some work like this, answer different questions using the values that you see in that contingency table, okay? But really, it all starts from, we're just looking at kind of frequencies and then really turning those into relative frequencies, okay? Any questions on any of this? Do you want to see a cell again or anything there? You okay with this? All right. So I have kind of the completed sheet already uploaded. It's in the same workbook. So when you see the union data file on Canvas, we just worked like from the blank one and kind of built it. But just as a check to what we were doing, here's this final one. You can kind of go and you'll find everything that we just recreated. So even if you didn't work along with me, you've got that there, okay? Oh, but I also wanted to mention one more thing. One thing that's kind of cool is the way I have this set up. Let's say like this was trying to get it like, you know, industries with like high union membership, having higher or above average differentials. Well, maybe I want to look like at really high union membership. So instead of 10, I'm like, well, let's look at 20, right? Really, really high union membership. If I change that cutoff, if I go back, notice it updates my frequencies, it updates all my probabilities, it updates all my work down here. So using these cell references is so useful because I can start to then play around with different cutoffs. Maybe I'm not just interested in high union membership, but really high. I don't know if I can go up as high as 70. Yeah, I was gonna say we probably start to get zeros there. Let's see if we can do 50. 50 is still too high. There we go, we do 30, we still have some zeros. So here, we would say that having differences less than $100 or 10% above, those would actually be mutually exclusive. We end up with a probability of 0. Okay. But I can play around with these cutoffs. The other thing I could do is maybe I just said, well, I tried to choose a number near the mean, but maybe I want to use the mean as my actual kind of cutoff, having above average or having below average. So if in my cutoff, or that cell that I was referencing where I had the cutoff, what if I did equals average and then took the average union membership? So I got the average in there, it updates everything as well. So it's really nice to kind of have those initial cells where we'll put these cutoffs in instead of like typing 10 in here every time. Well, then if I want to change that, I got to go back through and retype everything. Whereas if I use cell references, I just have to change one cell. Okay. All right, I think that's the only other thing I wanted to mention there. We got a couple minutes. I think I'll just start the idea and then we'll pick up on it next class. So we have all these probability rules that we're mainly using this one today, multiplication rule. Well, let's not forget about the addition rule, and then it's kind of this complement rule. Okay? So I'm going to go through this slide. I'm not even going to kind of waste time with it, but there's this huge kind of outside of this class, even outside the scope of this class, work with Bayes' theorem, and it's this idea that you have this event that you're interested in the probability of. You think that you know the probability that's going to occur. You run an experiment. You look at the outcome of that experiment and you use that information to update what you think. So the easiest way to think about this is like, if I thought the probability, oh, let's think of a good one. The probability that, I don't know, so we'll use a bad one, but like, let's say I don't know the probability that somebody could, I don't know, dunk on a 12-foot rim, right? Like just this insane thing, right? I think it's impossible. So I think the probability is 0. I then run an experiment where I see if the best basketball player in the world ever can do that, and then he does it. Well, I now know that it's possible, so I know the probability can't be 0. I still think it's relatively low if I choose a person at random that they could do that, but I'll update that probability to not be 0 and maybe be 0.0001, right? Because I've at least now seen an outcome that goes against my initial thought. Right? So that's the general idea of what we're doing here with Bayes' theorem. We're getting some additional information and we're updating the probability. So like it's kind of like a conditional probability that we're looking at. So the way we're going to set up all these Bayes' theorem problems and these Bayes examples is we're going to have two states of nature. Right? So we can call these S1 and S2, but they're basically complements of each other. Right? So you can think about this as we're going to be thinking about situations like, is somebody guilty or not guilty? They're either one of the two, right? Maybe we don't know for sure, but they are guilty or not guilty, right? Someone either has HIV or they don't, or they have COVID or they don't, right? Someone's either pregnant or they're not. Like there is some underlying state of nature that we might be interested in which one of these is true. Okay? And I'll actually probably update the slides before Friday, maybe do some COVID stuff. These events are exhaustive. So I'm basically saying, you're either guilty or not. So when we add those probabilities up, the probability should be 1, right? You're either pregnant or not. So if you add up the probability of each one of those events, it should add up to 1. Okay? Now, the problem is we usually can't truly know which state of nature someone might be. And so we're going to use some tests, right? We're going to run this experiment. We're going to give someone a test and then look at the outcomes of that test to help us update the probabilities of which state of nature they're in. Right? So, I don't know if someone starts to get sick. I don't know if they have COVID or not. I give them a test. If I see a positive test result, I might think the probability they have COVID is relatively high. If I see a negative test result, I think the probability is relatively low. However, if I see a positive test result, the probability that they have COVID now is not 100%, right? There are false positives, and just because I see them get a negative test result doesn't mean the probability they don't have it is 1. It's actually lower, right? There are also false negatives, okay? So I'm going to use the outcomes of this test to update my probability of whether or not they have this disease, but it's still not going to be 0 or 1, right? It's going to be somewhere in between. So what we're really thinking about is when we see the outcome of a test, I see the COVID test come up positive, E, well, now what's the probability that they actually have COVID, right? That the true state of nature is they have this disease, okay? So we're going to be looking for conditional probabilities, but it's not going to be as easy as what we were doing before, where we could simply, I don't know if I have it here. Yeah. It's not going to be as easy as simply taking the intersection of the two events and divide it by what we're conditioning on. And we'll dive a little bit more into why that is next class. We're going to have to do a little bit of work, a little bit of math here to kind of get this more complicated formula. And I'll walk through all this. Well, next class, we'll kind of start in this slide and how we actually get to this point and how we use this equation. But ultimately, what we're really looking at is just a conditional probability. We're using the outcome from some test that we ran to figure out what the true underlying state of nature is. Okay? So, some of this, right, should be on that Learn Smart assignment that I said I want you to make sure you go through. It's 5 or 6 minutes and do that before class on Friday. Okay? That's primarily what I'm using that for. I want you to take a look at some of the information that's related to kind of Bayes' theorem and some of the stuff before we kind of go over on Friday. And we'll probably start Friday. We might not finish it until Monday. I'll spend a good chunk of time on this, okay? Other than that, you have that Connect and Excel assignment due at the end of the day on Friday. A lot of you have kind of reached out for help for me with that. I've got a meeting with a couple of you this afternoon. So make sure you send me your questions on that. Other than that, if there's no questions for me, we'll end for today, and I'll see you guys on Friday.